phase behavior of a single component or pure substances and a mixture of two components. What if we have more than two components? What if we have multiple components, three components or more? If we have three components or more, we are going to use what we call ternary diagrams. The ternary diagrams are triangles which we can locate the lightest components at the top and the heaviest component on the lower bottom side of the triangle. Okay. So if I have three components, I put the lightest component at the top, second lightest component at the lower right part, and the heaviest component on the lower left side of the triangle. Okay. If I have more than three components, the way it works is we always put the lightest component at the top and then the second lightest component at the lower right side of the lateral, and then I will combine all other components and I'll put it right here. So I lump all the components heavier than the second lightest component and I call that, let's say, propane plus or heptane plus or whatever, the which is basically the summation of all the mole fractions of the heavier components than the second lightest component of the mixture. Okay. So the way this works is at every apex we have 100% of the component. So at point 1, at this point, right at the top, I have 100% of component A and 0% of component B and 0% of component C. At this point, B, I have 100% of component B, 0% component A, and 0% component C. And at this apex, I have 100% of component C and 0% A and B. So at every apex, I have 100% of the component associated with that, okay? For the rest of the areas, if I'm looking at this lateral, A, B, I have only a mixture of two components of A and B. On this lateral, I just have a mixture of component of A and C. And on this lateral, I just have a mixture of component of B and C, okay? And if I'm at somewhere in between, then I have the mixture of three components. And the way it works, from the point that I'm located, I can draw a perpendicular line to every one of these laterals, and then I can count, this length to find the percentage of the component associated with this point. So for example, if I'm at point 1, the point 1 is right at apex B. So I have 100% of component B, 0A and 0C. So at point 1, I have 100% of component B. If I'm at point 2, I'm in the left lateral. So in this lateral, I have, so this is 100% A, this is 0% A. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's divided into 10 parts. So each part is 10%. So I have 10%, 20%, and 30% of component A. So at point 2, I have 30% component A, therefore 80%, therefore 70% of component C, and 0% of component B. If I'm at point 3, then as I said, we're going to draw a perpendicular line to every one of these laterals. So if I draw a perpendicular line on this lateral I have 0% of component A. So this is 10% line, 20%, 30%, 40%, 50%, 60, 70, 80, 90, and 100. So point 3 is almost in the 10, 20, 30, 40, and 50%. So 3.3 includes 50% of component A. Or I can draw the perpendicular line and count this 10, 20, 30, 40, 50. So at point 3, I have 50% of component A. What about component B? Again, we draw a perpendicular line on the lateral in front of point B. I know at this lateral I have 0% of B. At this point I have 100, so it's 10, 20, 30. So I have 30% of component B, 50% component A, 30% component B. Definitely I should have 20% of component C, which is basically if I draw a perpendicular line, I can see this is 10% and 20%. So point 3 has 20% of C, 30% of B, and 50% of A. If I look at point, let's say 4, let's say this point, again, at this point, I can draw a perpendicular line. So at this point here, this lateral has 0% of A. So this is 10%, 20%. So I have 20% of A. For component B, again, this lateral has 0% component B, so this is 10 and 20. So I have 20% A, 20% B, therefore I would have 60% of C, which is like 10, 20, 30, 40, 50, and 60. So at any point, I can just draw a perpendicular line to the laterals and then count the steps to know how much of each component I have. Okay, so this is how we come up with the percentages. But the phase envelope in the ternary diagram is more complicated than the mixture of two components. In the ternary diagrams, the tie lines, the lines that were connecting the saturated liquid and saturated gas phases, are not parallel to these laterals. Okay, so this is one tie line, this is another tie line, this is another tie line, this is another tie line. So you can see these lines are not parallel. Okay, so if I want to find the quantities of gas and liquid at any point inside these phase envelopes, then I can still use the proportionality, but what I need to do is to actually take a roller and measure these lengths 1, 2, and 2, 3, or 1, 3, and 2, 3, exactly like how we were doing it for the two-phase mixture of two components. Okay, so we'll go over an example here, which is basically very similar to the example that we covered for the mixture of two components. This time we have a mixture of three components, and the question is, what is the composition of saturated liquid, what is the composition of saturated gas, and what is the quantities of gas and liquid at a specific point that we have the mixture. Okay, so here basically it says the mixture is 50% methane, 15% propane. So this is enough. If I know I have 50% methane and 15% propane, definitely I would have 35% of the third component, which in this case is N-pentane. So I have a mixture of methane, propane, and N-pentane. At what condition? Again, in the ternary diagrams, the pressure and temperatures are fixed, okay, because we don't have the luxury of having another, axis to show that. So the pressure and temperature is fixed. We don't have any other dimension. So pressure and temperature is fixed. Mixture is methane, propane, and N-pentane at 160 degrees Fahrenheit and 500 psi. So the mixture is given methane, propane, and N-pentane. I need to go to the book and find the ternary diagram corresponding to exact temperature and pressure given in the example. So this figure has a methane, propane, and N-pentane at exact temperature and pressure given in the example. So this is the ternary diagram that I'm going to work with. Okay. Again, methane, the lightest component at the top, and N-pentane, heaviest component in the left bottom of the triangle. Okay. So I have 50% of methane and 15% of the propane. This time, every one of these divisions are 5%. Okay. So I need to have 50% of methane. So this lateral in front of methane is a 0% methane. Then I have 20%, 40%, so 45 and 50. So this line is a 50% methane. So my point is somewhere on this line. So this is my 50% methane. Now I have 15% propane. So again, this lateral has 0% propane. So I have 5, 10, and 15. So where the 15% line of propane meets the 50% line of methane is my point. Definitely at this point we will have 35% of N-pentane. So I located my point in the ternary diagram. The second step is to draw the tie line. So if this point is falling exactly on one of the tie lines shown in the graph, then I use it. If not, then I'm going to use the closest tie line to that point. So here I'm going to draw this line parallel to the closest tie line to this point. So this tie line will hit the dew point line and the bubble point line in point 2 and 3. We know this is dew point line because it's closest to the lightest component, and this is bubble point line closest to the heavier components because the bubble point line is 100% liquid. It should be closer to the heavier components, and the dew point line is 100% gas, so it should be closest to the lightest component. So we have our tie line and we located our points. So the first thing is to find the composition of the saturated gas and saturated liquid. So this point 2 is my saturated gas. So the composition in the saturated gas is here is 0% methane, 20%, 40%, 60%. So 65, 70, it's between 70 to 75% of methane. So this is 74% to be precise. And then the amount of propane, again, this is 0%, so 5, 10, it's very close to the 15%, so it's 14% propane to be exact. So point 2 has a 74% methane and 14% propane. Therefore, it should have 20% of N-pentane. The summation should add up to 100. So as soon as I got 2, the third one is very easy to find. So that becomes the composition of my saturated gas. What about the composition of saturated liquid? So point 3 is at the bubble point line. So that's my liquid saturated liquid point. So again, point 3 on this lateral has a 0% methane. So 5%, 10%, it's between 10 to 15. So the precise number is 13%. So I have 13% of methane. Okay. What about the propane? Again, this line has a 0% propane. So 5% line, 10%, 15%, a little bit more than a 15, so the exact number is 17%. So 13% methane, 17% propane. So definitely I should have 70% of N-pentane on point 3. Okay. So how to read these? We are using these divisions. So every one of these divisions are 5%. So if you read this number for the methane like 13%, 14%, 12%, it's okay. But if you read this 17%, this is definitely not okay, because you have this flexibility within the range of the accuracy of the graph. Okay, so we locate the point, we draw the tie line parallel to the tie line shown in the graph, we get the saturated liquid and saturated gas, we read their compositions. Now we need to find the quantities of gas and liquid at point 1. I know here on the saturated gas, I have 0% liquid. At point 3, I have 100% liquid. So what's the amount of liquid at this point? This becomes the length of this 1, 2 over the length of 2, 3. So I actually take a roller and measure this length. I cannot use the numbers that I read here because the tie lines are not necessarily parallel to the laterals. Okay? So I measured this. This is 0.65 inches over 1.7 inch. So the amount of so I'm doing for the liquid, so this is for the liquid, so it's 0.42 inch over 1.07, and this is 0.393 pound of liquid per pound of mixture. For the gas, I know here I have 0% gas, here I have 100% gas. So the amount of gas at point 1 becomes 1,3 over 2,3. So 1,3 length, if I measure it by ruler, is 0.65 over 2,3, which is 1.07. It becomes 0.607 pound per pound of mixture. I know in this example, I have 6 pounds of mixture. So I need to multiply these numbers by 6 to get the actual quantities of gas and liquid at point 1. Okay? So it's very simple. We just need to follow the steps. And you need to expect this in your homework assignment and your exam. So just go over it one more time. And if you have any question, let me know. Okay. The last thing that we need to know about the Turner diagrams are how to draw them. Okay, how to draw the Turner diagrams if I have the pressure temperature diagram. Okay, generally this pressure temperature diagram we will get it from the lab. Okay, but if we have this, how do we able to plot the Turner diagram? This is also definitely one of your quiz exam, quiz questions or the exam questions. In this example, we have a mixture of methane, propane, and N-pentane. Okay, so we have the mixture of 3 components. So therefore, we should choose the Turner diagrams. And then we are going to change the temperature from point 1 and we go all the way to point 8. Or we start from the pressure of 1, then we go all the way to 8. And at every one of these locations, we wanted to know how the Turner diagram will look like. Okay, so this will be the discussion of the next part of this.